Hello and welcome to Advanced Machine Learning. In Module 6 in particular, I'm going to talk about cross-validation. This isn't something new. The terminology might be a little bit interesting, and I think there may be actually a little bit on the part of the course designers, a little bit of commingling of ideas. But we'll go ahead and talk about it as it's presented here, and then I'll probably add a little color along the way for completeness. So this module focuses on applying cross-learning methods for validation in the modeling process. So the idea here is that by the end of this module, hopefully you're able to utilize model validation techniques, explain the cross-learning method, and then apply cross-learning methods to real data sets. So let's start off with the concept of what is model validation, something that this course or this module is very much centered on and is quite relevant to the course. In order to evaluate the performance of any kind of a model, be it neural network or otherwise, you need to test it using some unseen data. This is a fundamental concept to where you may hold off a certain portion of the data and make sure that the model never sees it until you're actually doing validation. And the idea here is the testing provides a performance information that indicates if that model is underfitted, overfitted, or has a proper degree of fit. Cross-validation is a method used to test neural network models and other models as well to ensure that an effective output is reached. The best against introduction of over and underfitting is to use real-world data sets that mimic your environment as closely as possible. So synthetic data is problematic in this space. You typically want something that is real, that you're likely to see in the real world. You need to divide that data set into three segments essentially. So there's test, there's holdout, and then there's holdout set, and then the test set. So training, test, and holdout. The other words for that is sometimes training is training. We kind of know that. Sometimes there's essentially validation. That's what we're talking about with holdout here. And then the test set. During training, holdout might actually be somewhat used to determine how well you're doing. But at the end of it all, whenever you go to determine the true level of performance of your model, you do so with something it has never ever seen before. That's what the test set is. And it's essential that all the data sets are pulled from the same distribution and that they are close to the actual data that they will eventually be processed. Also make sure that the smaller percentage of your distribution of holdout and test set whenever there's a lot of data, right? So you may have smaller percentages, 1 or 2% even, if you've got a really, really big data set. And you may stick to something closer to 5 or 10%. The typical split is somewhere like 60-20-20 or 80-10-10. But the idea is that it is not a hard and fast rule. It is based upon the data, the situation, and so on. But as with things that kind of like the scientific method in general, you don't change it if it's not going well. So if you start off with your training and you do your split and you analyze your data sets to make sure that they're a reasonable distribution, that some weirdness didn't happen with your sampling and so on. And then at the end of it all, you don't do very well, maybe you overfit or underfit. You don't decide, well, let's reshuffle our data and try it again. Because that's kind of defeating the purpose. The purpose of doing this testing is to determine the generality of your model, of how well it does on things that it has not seen before. And that's an essential part of all machine learning, and in particular neural networks. So the basic idea here is to continue the discussion, the test, train, split approach. And this method uses the complete data, which is split into two groups. One group is for uh, basically it's called the training set, right? That's what you train on, and the other is your test set. The names are pretty common sense. The test set is for testing how well it does after training has completed. You may also do some splitting of that training set into another set, which is the validation set, which is used to evaluate how well you're doing as you're progressing through training. So at the end of each epoch, you may have a percentage of that that data that the model will be seeing during the process, that you determine how well you're doing on it. It's not necessarily indicative of how it's going to do overall, but it might let you know when it's time to stop your training, or when you've overtrained, and maybe you need to back up a little bit. The splits are generally something like 70-30 or 80-20, but it really depends on the amount of data you have. If it's if you don't have much data, you can have a lot more bias, and that's the concern. You need adequate data for training. That being said, you're better off with a better but maybe smaller data set for both training and testing than you are a large data set that maybe isn't so good. So you're better off making sure that it's a clean corpus that you're using to do your training, rather than it's just a bunch of data, right? So more data is not always better data. So you want to make sure that the data is accurate that you're using, because we're here primarily, we're talking about, obviously, it's labeled data because you're doing, uh, you know the answer ahead of time. And if it's wrong, meaning you say that this is a picture of a cat but it's actually an owl, then that's a problem, right? So in either of your sets, if it's your test set, it's going to give you a poorer performance than perhaps you should have. If it's in your training set, it's going to really confuse the model. So those are concepts to keep in mind. You also want to make sure that the distributions are the same. That means that you're sampling in a random fashion, and that there's no inherent kind of bias in the sets that you're producing. You also want to make sure that in general you've got a nice distribution to your data. Uh, you also want to make sure that as the amount of data gets bigger, the percentages that you need may get smaller, and that's because you don't necessarily need quite as much to ascertain how well you're doing as you do potentially to train. You will find that train test split in the Python scikit-learn library is your friend. You want to use that. It is an excellent library. It does exactly what you need, which is ensure that your data is split into at least two groups with a certain distribution. And most libraries have some fashion of doing that, but that's one that's in particularly very good. Another approach that is sometimes used is this concept of cross-validation, in particular k-fold cross-validation. This is not, again, a new concept. We talk about it in lots of classes. The basic idea here is that you have a relatively small amount of data. And what you do is that on each kind of iteration through the experience, you take a percentage of it, and you basically split it into buckets, and then one bucket is your test set for a given iteration, and the others are your training. And then on the next iteration, that bucket moves down the line to the next whatever percentage, so 25% or whatever it might be, and then you use that for your test set, and the remainder is your training set, and so on. You're reusing the data that you have in a way such that you aren't explicitly violating the rule of training and testing separation, but it's not ideal, and you only should do this if you don't have enough data to do it the proper way. But it is something that can be done whenever the data is limited. It's ideal to split the data set into sets, and then one set is for test while the others are training, and you iterate through those sets in a combination sort of way. At the end of it all, you end up with a pretty good approximation of the overall process or approach that you're wanting to use. Another look at that is to take a look at this kind of as a textual sort of format. So you have k-folds that we're using. So k is the number of buckets, if you will, or partitions. So you take it and split it into 4 different buckets in this example. The first iteration, fold 1, is our test set, and folds 2, 3, and 4 are our training. We move on to the second set, and fold 2 becomes our test set, and 1, 3, and 4 become our training set, and so on. So K is simply the number of folds or buckets or partitions, pick your word. But it is, in that sense, it's a number of the things that is going to give you a sense of how many different variations you can have. Obviously, the higher the number of Ks, potentially the larger set of combinations, but at the same time you're making them much smaller, so you may suffer if you do that as well. A relatively small number of K is fairly common, um, and it is something that's used in some of these neural network training processes, especially if you have limited data. And again, this is not a new concept. Maybe you haven't thought of it from a perspective uh, of neural network training, but it isn't new. So whenever you're not to, I guess, to stress it overly, it is important that you're using real data that is accurately labeled when you're doing this stuff. You don't use artificial data. You don't do some sort of production of it or whatever else. You want it to be data that is similar to the data that you're going to see in the real world. So that's so that you can evaluate how well it's actually going to do. And also it's critical that it's being done against unseen data. You can think of it in terms of what a neural network does under the covers is essentially fit a curve to a set of points. You can think of it as that way, or take it into higher dimensions, a hyperplane to a series of data points. And so if you give it data and it sees things and it fits to it, it would make sense that it's going to do really well with the data it's seen before because it's adjusted its weight so that it does well. The problem with that is it may be artificial in nature in that it's overfitted or underfitted the actual curve. So it may be that the better approach is to not necessarily map it directly to the points, but get in the neighborhood of the points, right? And so then whenever you see points that you haven't seen before, you're going to do better dealing with them than if you've met exactly to the ones that you're trying to do. Uh, and the way we do to ensure that that's done is by this concept of cross validation, so that we're doing the holdout set, we're making sure it's never been seen before, and so on. But there are some caveats that you have to think about whenever you're doing this approach. High quality data set should be clutter-free and as clean as possible. That means you shouldn't have duplications. You shouldn't have mislabeled or inappropriate values. They likely should be on a similar sort of scale, and so on. The amount of energy and time you spend labeling this data set for your supervised learning can be considerable, and it can be quite expensive. So you might be tempted to take 3 or 4 different data sets, stick them all together, and think it's going to work out. Uh, Especially if those are taken in different ways, labeled in a different way, it can be very problematic. So you can't just take a labeled data set in one domain and stick it together with another labeled data set and not do some work to make sure that things are similar and hope it's going to work out. They should be easy to use. It's a good practice to look for data sets that are fairly simple, if it's possible, and do not contain an abundant amount of rows and columns. Also, interestingly enough, sometimes things like images, smaller is better. And in fact, sometimes whenever you're doing this stuff, part of the process is reducing the fidelity of the image or whatever to something that's less than what it was, because it basically is reducing the dimensionality. Uh, Cleaning a large data set is very time consuming. I can say this from personal experience. Uh, you need to consider the concept here that suppose you have a data set with 100 records in it that are labeled a certain way. If 10 of them are wrong, that means there's a 10% error and 90% accuracy within your known universe of test and train. What that means is the best you could possibly hope for from your algorithm is 10%. Probably you're not going to get to 10% accuracy anyway because there's a certain amount of noise and error and whatever else that goes on each time you deal with a particular um, training activity and so on. You don't get 100% generally speaking with a neural network sort of approach or any sort of machine learning approach. There's a certain percentage. So you may, if your accuracy of your overall data sets is only 90%, you may only get to 80 or 85% because of the other types of error that may be contributing. So you do want to keep that in mind, that the degree of your overall success is going to be impacted tremendously by the essentially the accuracy of the data that you're using to train and test with. And testing can be as, if not more important, than your training set. It's also important to consider how it is that you're deciding what something is. So imagine you have audio recordings and you have corresponding transcripts, and say you have 100 of those, right? You could partition based upon 3 or 10 of those transcripts or 20 of those transcripts become your test set, and the remaining are your training set. The problem you have is that perhaps those 20 that you're using have interesting language compared to the others. Maybe there's a lack of representation in your training set of a certain accent, or maybe it's the other way around. There's no accents in your training set or your test set. So you need to make sure, again, that how you're carving up test versus train is thoughtful. Perhaps it should be based upon, I don't know, if in the case of a transcript, maybe it's sentences, or maybe it's blocks of distinguishable time, so essentially paragraphs, or if you know who's speaking, maybe it's randomly selected amongst the various speakers and all of the things, and you pull out a certain instance of each utterance by a particular person, and that becomes the way of deciding what is test and what is train and what is an item in your data set. So simply put, you need to make sure that you know the accuracy and do a proper assessment of your data sets before you get very far in the rest of your research or your analytics. Some algorithms may do better with less data than others. Some might do better doing some other approaches, such as transfer learning, which is different than what we're talking about here, but is relevant to this course and really should be discussed. Transfer learning is this concept that you take a model and train it and test it in one domain. And then you use that pre-trained model and augment it in some fashion with additional layers of training on top of it, or additional layers on top of it, and so on. So an example might be you train a model to recognize traffic signs or something. You then take that pre-trained model and then apply it to recognizing something else that isn't traffic signs, but happens to be something that works out. And this happens more than you think. It might be that a handwriting recognition algorithm might do something very well in some other space. And doing transfer learning is very important. A very common instance of this is to take a model that is perhaps trained on a generic corpus, say just natural language that people typically utter of a certain level of education, and then apply another sort of reinforcement learning on top of it, or additional learnings on top of it. Reinforcement's the wrong word because that means something else. But you do some additional training with a specialized sort of corpus. So maybe you add in some legal terms because you want to be able to recognize legal terms. So you take a model that does pretty well with generic language in general, and then apply some specific case that you're interested in. And then you take your test set that is part of what you'd use to do that kind of transfer learning, and see how it does in general against it, as well as testing it against regular words. So those are things that you need to consider when you're talking about data sets. So an example is doing K-fold with iris. I'll go ahead and open that up. You've seen iris dataset quite a few times. It's made up of a set of flowers and different species, 3 different species of iris flowers that are distinguished by the measurements of those flowers. And you can see some nice little graphs here along the way. So we'll go ahead and pull it down from a GitHub repository that I have and plot it out. And you can kind of see the various ways that they might be split out based upon combinations of values and so on. So again, this is a fairly well-known, I'm sure you've seen it before, problem. We can take a look at the columns, take a look at how much data we have, and it's roughly 150 rows, right? So by 5 columns. So we can do our typical sort of X and Y thing. So we're saying, well, we're going to try to target, figure out what Y is, which is the flower's particular whatever it is species, and then the X is the attributes that are useful to try to determine that. We can take a look and see what X looks like, and we can see that it's 0 to 49, so 150 rows. Uh, One of the things you've probably seen so far is this concept of a one-hot encoder. What one-hot encoder does is takes something that's essentially categorical in nature and turns it into essentially a byte array. So the idea being that the values are not strings, so it's no longer this name of the species, but it turns into a vector instead that can be then used to determine. And to do that, uh, you can see it's basically as simple as the typical, you create a label encoder, you basically call fit on Y and get back the results after doing the transform, and then essentially run it to to turn it into a categorical value again. So it's one if it's the whatever the first species was, Setosa, and so on. So and the last one is one if it's the other. It's an exclusive thing. You're only going to have one byte on, so that's why it's called one hot encoder, right? So one is hot, the others are not. And so the idea is that it simplifies the process of doing the actual classification. So we can start off with a k-fold approach. We're going to take k is 5 in this case. We're going to give it our we're going to go ahead and essentially create the k-fold. We define our model, which is basically a sequential model of some dense layers, and then we're going to compile it. I think I hit anything. And so then we can, again, take a look at X. And then here's where we actually kind of do the work that needs to be done. We're going through the test and train for the various folds. So that means that we are having for each one of them, one is going to be the test and the others are going to be the train, and it's going to move like what we just talked about previously. Then we're going to go through and try to fit each one of those and then test as we go. And then plot out the results. And it's probably going to take a bit. Yeah, we're up here. We're waiting through the various folds. We start off at 95% on training accuracy, and testing is doing actually better on some of these 96.67. It's basically going through and doing our various folds. And then we can plot the results. And so we can kind of see some of the concept here of how the whole test score is going. So that's basically a real world application of k-fold. And again, this is not something you do casually. You do so whenever you suspect that there's not quite enough data. I'm going to pause for 1 second. I will be right back. As soon as I find the right app. Continuing our conversation. So again, the point of k-fold is to be able to make do with what data you have. That's the gist of it all. It's not ideal, but we don't live in an ideal world. Sometimes you don't have the budget to go and have a bunch of data trained. Sometimes you are labeled. Sometimes you just have to deal with what you have, and it's an approximation of how to do it. It is a distinct concept from transfer learning, which is the idea of taking something you learn in one domain and apply it to something else. That's a very important topic to discuss from a machine learning perspective because it's quite powerful. You can take these pre-trained models that do pretty well on lots of stuff, strip off a layer or two, stick on a different layer or two, do some additional training, and end up with some really cool stuff. So it is important to consider. Moving on to deliverables 6 and 7. Deliverable 6, which goes with module 6 obviously, is to apply cross-learning methods for validation in the modeling process. So you're a chief data scientist for Reliable Dynamics Inc., and they still create robots and do a manufacturing operation. You need to ensure that the company's various lines of robots operate consistently given a standard set of data. So you determine that the best way to validate any given operation is to use the cross-learning method. High quality products that operate safely is what has given your company a competitive edge, and it wants to stay ahead in the robotics world. Yes, we don't like dangerous robots. So your instruction is to, in order to uphold the company's high standards, you need to validate that every robot that leaves the RDI plant has passed critical diagnostic testing. You need to ensure that every robot is consistent in identifying similar patterns from a wide variety of test data. To do this, you must explain and utilize the model validation in your own example, in an example of your own choosing. Explain the cross-learning method. Use Python to apply cross-learning methods into real data sets. And then your report should be in the form of a Word document containing screenshots from Python where appropriate. So you're writing a paper, but you're also writing some Python code, and you're going to include the Python code inside of your paper. There's 4 rubrics here. So a thorough and detailed discussion has been developed on utilization of model validation is present with well-developed and accurate examples. There's a thorough and detailed discussion that's been developed that explains the cross-learning method uh, uh, and is well developed with accurate examples. Again, cross-learning method in this context is the test, train, validate, split approach that I've talked about. A thorough and detailed discussion has been developed on the application of cross-learning methods into real data sets. And then a thorough and detailed discussion has been developed on the application of cross-learning methods to real data sets through the use of Python. So a nice clean Python example similar to what I did with Iris is acceptable. Moving on to deliverable 7. This is the entire sort of capstone. So the competency is to be able to explain the idea of an artificial neural network, design a neural network algorithm using observational data, that is labeled data, apply deep learning methods for classification of data sets. Remember, deep learning just means there's 2 or more hidden layers. Apply supporting vector machines, so SVM for classification of data sets, and then apply genetic programming and genetic algorithms when handling a large data set. And then lastly, what we just talked about is applying cross-learning methods for validation in the modeling process. Scenario, you work now at Big Heads International or Incorporated. It's a universal think tank that offers its services to any company in the world. Probably not any company in the world because those whole pesky rogue state laws and such. But anyway, BHI is known for its out-of-the-box solutions that have saved or generated large sums of money for its clientele. Its services are not cheap, but its customers have reaped much more than what they have sowed. So basically it just costs less than they make or recoup. As chief in the machine learning department, chief probably architect or something, you have been tasked to develop a white paper, also known as a technical document, which delves into all the aspects involved in planning, designing, building, operating, and evaluating machine learning. Your white paper will be used as the foundation for future company to client interactions that encompass machine learning. Your instructions. In order to have a well-balanced artifact, you will synthesize the various concepts, components, and methodologies listed below that address machine learning. The results of your work will be in the form of a white paper created in Word and include screenshots from Python where appropriate. Your white paper needs to have a thoughtful flow, be comprehensive, and follow APA formatting rules. So evaluate concepts of neurons, nodes, layers, and appraise how artificial neural networks work and learn. Explain the backpropagation process and gradient descent, and then assess the typical results of each step in neural network and describe the nature of training and test data sets. Explain how convolutional neural networks provide robots with eyesight, the ability to detect and recognize things. Use Python to design or an appropriate number of layers and nodes for real data sets and apply deep neural networks to the grasping data set found. You don't have to do that. Interpret the results of this deep neural network. Explain support vector machines and apply them in practice using Python. Explain what a kernel, a regulation gamma, and margin are with regards to SVNs. Produce examples of genetic algorithms and genetic programs. Use Python to design and implement an appropriate data structure for genetic programs to implement a problem of your own choosing, and then determine an appropriate performance function for a real-world problem, and then utilize Python model validation and explain cross-learning methods and apply cross-learning method to a data set of your own choosing. The rubric, and there are, I believe, 6 in this one. The first one is a thorough and detailed evaluation and assessment has been developed that explains the concepts of neurons, nodes, layers, and assesses typical results of each step in neural networks. Uh, and then a thorough and detailed explanation of backpropagation process, gradient descent, and convolutional neural networks. And then a thorough and detailed explanation of support vector machines and what a kernel is, regulation gamma, and margin tuning parameters, as well as some examples. A thorough and detailed use of Python has been used to design and implement an appropriate data structure along with utilization model validation that explains the cross-learning methods is present and accurate, and then a thorough and detailed example of genetic algorithms and genetic programs, and then a thorough and detailed determination of an appropriate performance function for a real-world problem is presented that goes with genetic algorithms as well. So with that, we've reached the end of our discussion of the 7th deliverable and the 6th module and 6th deliverable. As always, if you have any questions, let me know. That's what I'm here for. Stay safe, and we'll speak again soon.